Thanks. Welcome back, everyone. So this is part three. We've gone through four of the different forms of parallelism. And so just for a super quick recap, um, when we are training a model, in particular, we're training in an LM, we have different components that are the main things that take up GPU memory. We have the parameters of the model, and this profile shows those parameters at the bottom in this sort of teal blue color. We have optimizer state. So typically, if you're using something like Atom, it's going to store two floating point numbers for each parameter that you have. So actually, approximately, depending on the different size floating point you use, take twice as much memory as your parameters. You're going to have gradients that you calculate in order to do back propagation. And then the really big one, those first three things, they all scale with the number of parameters. But then you're going to have the activations that are used to calculate the gradients. And in the case of an LLM, because every token position is sharing weights and everything, that doesn't explode the first three things. But the activations do, in fact, scale with the context length. So if you go from 4,000 to 16,000, the memory for your parameter stays the same, optimizer stays the same, activations, depending on how you, sorry, gradients, depending on how you do it, will be largely the same. But going from 4,000 to 16,000, the memory you need for activations quadruples. And so not only are the really large LLMs big in terms of the parameters and associated memory, but now as we do longer context length, this is why we've been talking about you really just flat out cannot fit this on one GPU or eight GPUs or whatever. You need a very large number of GPUs. More GPUs also helps you train it faster, but there's a certain minimum that you need given the size of a model. So if you think about the data going into an LLM during training, being this multi-dimensional tensor, where one dimension is the batch size, another dimension is the data size. So this is after the tokens have been embedded, and so that's the model dimension size. And then third dimension would be the sequence length. So what we've talked about is in the previous two sessions is a few different ways in which you can split all this information across GPUs. So the first thing was data parallelism, and that's where you basically split along the batch dimensions. So you're sending different samples to different GPUs. The next technique was tensor parallelism, where you're splitting along the model dimension. And so if you have a 1,000 float hidden dimension, if you have four GPUs, you might be able to send 256 to each GPU. And of course, there's times when they need to talk to each other, right? In particular for the attention. That's where ring attention came up. Context parallelism is basically then where along the sequence length you divide things. And so you can say if my max sequence length is 16,000 and I have eight GPUs, maybe I send 2,000 tokens into each GPU. And once again, there's times when they need to talk to each other to do gradient updates and things like that. And then the fourth one that we talked about is pipeline parallelism, which isn't really along the data dimensions, but just the fact that your model has layers. And so it's pretty easy to just split it between layers, and you can divide things up that way. There's complications with all of these schemes, but pretty much any model, whether it's an LLM or any other model, is going to have layers. It's going to have all of these things, and so you can do these four different degrees of parallelism on all these models. Yeah, Roger.
Oh, sorry, I wanted that to wait until you were done talking. I had a question about this image when you get a chance, when we get to a good point.
Okay. Yeah. Why don't we go ahead? Go ahead with your
Okay,
question.
it's just something I noticed that I hadn't noticed last time. This plateau in the middle, when we talked about like how pipeline parallelism and whatnot works, I was just trying to understand what would create a plateau there.
Are you talking about like between steps?
No, not so that's the optimizer, I think, right? Um, but see that as you're coming down in your uh, essentially, what are you doing? You're taking the activations and using them during the backward pass.
Hmm. So like maybe this little
Yeah, why does it
already.
flatten?
Yeah, I don't know. They didn't say what different settings they had when this particular profile was taken. So
Yeah,
there's things about this that uh, are not very clear. Perhaps there was some communication happening here, and that's why you don't
yeah,
see it going down. Because as soon as you've fully uh, uh, calculated all the gradients for a layer and you're moving on to the next layer below, you should be able to free up the activations from that layer. So you
yeah.
would expect to see it sort of monotonically decreasing and it wouldn't just sort of flatten. Um, there's no there's no point in an LLM where you don't have activations that you'd be freeing up.
Right.
So yeah, I think most likely this is some kind of example where there's a whole bunch of communication
Communication.
happening, maybe halfway through.
Yeah.
So maybe
Or
it
maybe a
is,
steady state in the middle or something like that.
maybe there is something here with pipeline parallelism.
Right.
Some kind of
Yeah.
bubble got created in there.
Yeah. Yeah. That's what I
Yep.
was thinking maybe too. Okay. Thank you.
Yeah. So in this article, we're going to have one more, which is pretty today, which is pretty much unique to LLMs, and you won't be able to use it all the time. These four can be used all the time, although it varies whether or not you want to use all of them. Data parallelism, like we talked about, is the easy one. Okay, you can do a couple settings in PyTorch, a couple lines of your code, and just basically activate data parallelism. Okay, whether it's vanilla data parallelism, like I'm just going to have 8 GPUs and I'm just going to run 8 times as much data, and each one's just going to do its own thing, um, or whether you start actually splitting things up to save memory to the point where we talked about fully sharded data parallelism. FSDP is now available in PyTorch. The others require you to actually refactor and write code and stuff. So if you today, there's no really nice automated way where in 1, 2 lines of code you can just say, hey, do tensor parallelism on my whole model, do context parallelism, do pipeline parallelism. Okay. Um, the other thing I wanted to mention, which applies to these four and plus the fifth one that we're about to get to, is that all of these parallelism techniques also work for inference. They're not exclusive to training. The reason why you might not see as many articles is they're actually much simpler when you're doing inference, because the problem with training is that memory grows as you store all these activations. And and when you're doing training, the fact that the forward pass goes through the layers one way, but the backward pass goes through the other, means that it's just very hard to get the timing and all of these things right. Whereas when you're doing inference, you don't ever need to keep anything. As soon as you finish one layer, as soon as you finish any calculation, you don't need the parameters, you don't need whatever. And so it is possible, if you're trading speed, if you're willing to run slower at inference time, you can pretty much split anything any way that you want. It just might be a little bit slower. So, like hypothetically, for pipeline parallelism, if you only had one GPU and you just didn't have that much VRAM, you could load one layer, do the calculation, pause, get rid of that layer, load the next layer, do that calculation, pause. It would be very slow compared to when we, can fit the whole model. But technically, all of those things are available. And that's really not an option. It's even worse of an option if you're doing training, because then you have all this extra business of optimizer state and activations that you also would potentially be offloading and reloading. And so not only would it be slower than if you didn't do it, but it would be a lot slower, to the extent that all this stuff is, let's say, 20 times as much uh, memory as your parameters, then that's 20 times as much stuff that you would be, offloading and doing things like that. But you definitely will see when people are, doing lots of servers because you have lots of customers that want to use your LLMs, they absolutely, um, data parallelism is a no-brainer, right? You just send different customers to different servers, right? But people are doing tensor parallelism, people are doing pipeline parallelism. And the pipeline parallelism gets really complicated with the zero bubble stuff we talk about because you're trying to time the forward and the backward passes. When you're doing inference, you can just simply say, I have the first few layers on as many will fit on one GPU, and then the next layers, next few layers, next few layers, and you can just go sequentially through a bunch of different GPUs until you get your final answer and you send it back to the user. There's no complication because there's no backward pass and you don't need to store anything in memory. Okay. KV cache is just the only limitation there, just in terms of how much memory on each GPU. So all of these techniques do apply. It's just you don't need as in-depth of an article because they're actually much easier. All right. So with that, I think we'll just briefly talk about our fifth parallelism, which is expert parallelism, and then we can go into some of the, as time permits, some of the later material in the article, and then we'll be all done. So if you're familiar with Mixtral and the DeepSeek V2, V3 models, R1, they all use this technique called mixture of experts. We're not going to spend a lot of time, talking about what is this MOE architecture. We've talked about it some in the past. But the basic idea is instead of having one giant MLP layer, you have a switch that decides for a given token where it's going to go, and you have many, many smaller MLP layers. And this is an idea that makes sense because we know that MLP activations tend to be very sparse. So the reality is when you do send a token to the big MLP in the traditional LLM, we're actually mostly going to get a bunch of zeros out of it, and only a tiny portion of it might be contributing some non-zero values. So if there's only a tiny portion needed, then theoretically, instead of having one giant MLP, we can actually have a bunch of different ones, and we only need to route it to a subset. What's not obvious about whether or not this technique would work is, do you know how to route it to the right MLP? Okay, but we're not going to go deep into that. The main idea, though, is that especially if you have something like the DeepSeek architecture, where we have lots and lots of experts. So if I have 200 experts, and I'm only using, let's say, I think it's a little bit more than that in DeepSeek, but for simplicity, I'm only using 4 at a time. And if I'm even luckier and those 4 are all contiguous, then it would be really great to just stick those 4 on one GPU and have the other 196 spread out amongst a bunch of other GPUs. And so basically what happens is when I'm processing this particular token, I can go to one GPU, get those 4 experts, and all my other GPUs can be handling other customers at the same time. So because of this router business, as long as we have really balanced load, where, again, if you have 200 experts, 4 per GPU, that would be, I think, 50 GPUs, each with 4 experts. As long as the load is split very evenly, 1/50th, it's super easy to do expert parallelism with degree 50 and just spread out the load amongst all those different. So this will not improve the latency on any one given inference. But it does mean if you have a high volume of customers, like OpenAI does, like now DeepSeek with all the publicity they do, it's very easy for you to spread the load amongst all those different GPUs. So that's in a nutshell how the expert parallelism works. And I don't think they have any, they don't have any other fancier diagrams, but just basically this idea that we're routing to different experts, and so we just spread the experts out over different GPUs. Any questions about expert parallelism?
Um, can I ask one question?
Of course.
So if we know that the feed-forward networks are sparse, didn't we just like make them smaller?
Uh, Sorry, they are sparse activations for any one given token. But if you combine the activations of all the different tokens that it sees, then it eventually sums up to a dense level of activations.
Oh, I see. Thank you.
Yeah. So it's not that 1 in a million ever activates. It's for this token, it's this 1 in a million. And for that one, it's that one. And, blah, blah, blah. And by the time you use, all the possible sentences and stuff, then actually everything, probably not everything, but like, a dense amount of them activate at some point.
Yeah, but if you like search through the weights of the network, and if some weights are actually gone down to zero, we can probably remove them and like save some memory or something.
Mhm. Yeah, and all deep neural networks are to some degree, sparse where you can get rid of stuff. But really where things happens is not that the weights are zero, but rather that the input in, if you consider it a vector space, is orthogonal or virtually super close to orthogonal to a given column in a weight matrix. And so when that happens, when you dot them together, you just get something very close to zero. But a different input token would have a strong closer to one dot product, and therefore it would actually need that. So that's why you can't necessarily just throw away columns. But for any one given token, if you're able to route it correctly, you really only usually need a handful of columns at most.
Okay, thank you.
Yeah, it's a great question. All right, so then the article says, hey, in a nutshell, we've got these 5 degrees of parallelism, and kind of like I was saying, data parallelism along the batch dimension, tensor parallelism along the hidden dimension or the model dimension, uh, what they called sequence context parallelism is along the token sequence length dimension, pipeline parallelism along the model layers, and expert parallelism along experts. And so anytime you're doing data parallelism, we have these levels of, do we keep copies on all the GPUs, or do we actually partition, do we shard some of the memory we needed across the different GPUs? So I wasn't planning on covering in too much detail, but basically they, after some more of their pretty diagrams, talk about, hey, we did a bunch of experiments and we found for, let's say, a 8 billion parameter sized model, if you have different multiple 8 H100 GPU nodes, what would be the fastest way to train it? Which parallelisms would you use? You would use some, you wouldn't use others, and eventually they have uh, uh, like a table here where, I know on your screen it's an eye chart, you're not going to be able to read it, but if you go into the article, then you'll see for this configuration, this is what they used. And in many cases, you'll see it's like, oh, we didn't use tensor parallelism at all. Oh, we didn't use context parallelism at all. When you get to really big, really long sequence, then they're going to end up using all of them. But in many cases, for this at the smaller end, they're just using a subset. And again, this is because there's this communication overhead that we pay for using the parallelism. So if you don't need that parallelism, then you're better off not using it. And in the case of tensor parallelism, we have communication which cannot be overlapped with computation. So that's the real killer with tensor parallelism. And I'm not 100% sure, but I think you're going to see they never go tensor parallelism above 8 because it was something like a 40% penalty to go from 8 to 16. So, if you're slowing things down almost in half, then it's pretty much never going to be.
Sorry, I have a comment about that. Isn't it because they're training the llama model and it has the group query attention size of 8, and you cannot like tensor parallelize more than the group query size? There's like a limitation like that, or something.
Yes, when we talked about that's another limitation, that it's really cheap to split the different attention heads on different GPUs. Once you split, try to split a single attention head over multiple GPUs, there's so much communication involved that, as far as I know, nobody has tried to do that in practice. It's a great comment. Yeah. So not going to go through all of this, but basically you can see here they have some general rules of thumb. It says if you're GPU poor, then basically what this means is you don't have a lot of GPUs, so you're not optimizing for speed. You're just trying to do the minimum necessary to see if you can even fit the model in memory and train it, no matter how slow. Okay. And so they say the tricks that you're almost assuredly going to use are activation recomputation, which is going to save you massive amounts of memory. Um, and then you can also use gradient accumulation if you're trying to do a larger batch size. For people who have lots of GPUs, which I wish you all that you might be in this situation at some point in your life, where you're like, hey, I've got 10,000 or 100,000 GPUs. Um, then they have some general rules, right? So like for small models, they fit in GPUs really well. And so they say you can just use a single parallelism technique, you know. So you can use just tensor parallelism, or you can just use data parallelism with the full zero FSTP sharding, whatever. When they say when the models get a little bit bigger, then you see where their recommendations they found what was fastest was combining a couple techniques. When you start getting really big, like over 500 GPUs, then they say certain things start to become inefficient due to the communication cost. And so this is where you're better off adding other parallelism schemes. And then finally, they say, hey, if you're really rich, you're now talking about the thousands of GPUs. What they found was tensor parallelism level 8, which in their case, that's because they have the super fast communication between GPUs on the same node. Okay. Data parallelism 0, 2, and then go ahead and use pipeline parallelism. So again, there's like, certain details, but you can see here that they're not using, all of these. And then I think the other thing is, if you have a mixture of experts model, you always want to use expert parallelism. It's not really stated here, but it's kind of just orthogonal to the other four. Yeah, and so I don't necessarily expect to ever be in the 1,000+ GPU position where I'm training large LLMs on that large of a cluster. But I did find that this article was really helpful in going through, the different basics and explaining what the different parallelism mechanisms are, and why you achieve slowdown when you go higher, and how you can try and hide the communication by overlapping it, and to what degree you can. So ultimately, that's sort of where we get to the end of the main article before we get to the appendixes. So any additional questions or comments about this material and the 5D parallelism that they've explained?
Ed, so I'm curious because at the beginning I thought we were kind of dismissing like tensor parallelism would be the last thing you do. And yet it shows up in the recommendation numerous times.
I'm not really sure, but I think it's because these guys, so all of these recommendations change depending on what your hardware is. Okay.
Right,
So
right,
these guys were training on nodes that had 8 H100 GPUs with, I guess, the NVLink.
right.
And that NVLink is so fast that even when you don't hide the tensor parallelism computation, there's really minuscule penalty.
Yeah, yeah. I was looking that up. The NVLink 5, which is the highest spec, I don't know how many are implemented at that level, is 1.8 terabytes per second
Yeah.
aggregate.
And I think you can have like all the GPUs simultaneously using that 1.5 terabytes to exchange everything they need to exchange, and then they start doing computation again.
Yeah, it was. Yeah, okay. I wasn't sure how I was reading it. I thought that meant like the aggregate of all of them, but
No. It might be
could have been.
aggregate, but
It
what
might
I'm
have.
saying is that there's no need for them to sort of like wait. Like they can,
Yeah,
they can. If you have 8 of them, then they can access whatever zero point 0.2 of that each,
yeah,
all simultaneously, and sending data wherever they want.
yeah.
Like
Yeah,
full switch mode.
I think I missed the value of the NV link that boy, it's so much faster than the other ones that it really allows you to almost have shared memory amongst
Yeah,
all of the GPUs in your chassis.
I think that's the gist. Is that it just makes it
Oh,
so cheap.
Yeah.
okay. So I have one more question. So it's because like in case of like TP versus PP, right? Tensor parallelism versus pipeline parallelism, you're gonna have more communication in case of tensor parallelism compared to like pipeline parallelism, right? Among GPUs. Even though like NVLink is like 1 terabyte or something, it's slow compared to the GPUs, right? Because the GPUs are in like hundreds of teraflops, like if I'm not mistaken, like 1,000 teraflops or something. So it's slow, right? So which one would be faster, like to parallelize across tensors or like to parallelize like in a pipeline?
Yeah, and
I
I'm not doing these. I'm right. I'm covering the articles. So basically, just everything I'm doing. What's that they say in the TV shows, right? That's hearsay, right? Because you just heard somebody else say it, right? So I'm parroting back what they say, and so really you can look at their recommendations here, where they tried it different ways. They said, what if I just use pipeline parallelism? What if I just use tensor parallelism? Um, what I can share is though that if you remember the pipeline parallelism, it makes a lot of sense just in terms of like, oh, I'll do layer 1 through 4 on one GPU, and I'll do layers 5 through 8 on the next GPU. Um, but then you have to wait until the backward pass, and so that's where you start getting these crazy diagrams like this, where how do you split things up between the forward and the backward pass, the different layers. And so it's just not that easy to do pipeline parallelism. So one possible answer is that pipeline parallelism, if you time it and you balance it and you get it just right, maybe it does beat tensor parallelism, but it's way wicked harder to do all of that work right now. Someday there may be a library that just automatically figures it out for you. So I think that I'm guessing that that might be part of the reason why tensor parallelism is used, because it's just so much easier than having to figure out this, zero bubble type stuff, which is going to be different depending on your model and your GPUs. So just the fact that the Llama 3 team figured this out, if you have different GPUs or if you're doing a different model, you can't just reuse what they did.
It does feel like something that should be automatable though.
Yeah,
Like just run the calculations. They're the same each time you do it, and measure them, and then shuffle them around until you get at least the fewest number of bubbles in there.
yeah. I think a year from now, you may be able to get all these parallelisms with just a couple lines and saying,
Yeah.
please automate this.
Like I'm working on it. Like we're building library like that at the
Oh,
moment.
cool.
What libraries are those?
So there's like the framework called Megatron LM. So you
Oh
can
yeah, yeah.
implement all of these techniques using that. And we're like trying to automate what would be the best thing for you. You're like what kind of depending on the model you're training, what would be the best techniques to use, I guess.
Cool.
Yeah, and if you look in this article, they have places where, God, I'm trying to find one, where they have sample code and they say, hey, in Picotron, here's like some sample code or whatever. And I have a friend who was trying to train a long sequence model, and he said, yeah, even with the sample code, wasn't like, oh, I used their sample code, and it was rough. Hey Dave, thanks for your patience. You have your hand raised?
Yeah, I have a comment on the comment that um, Roger asked, or question that he asked. So, is tensor parallelism the first option chosen if there are matrix multiplication that will never fit on a GPU, then you have no choice but to start with that. So it depends on the size of your model and other parameters. But then if that's the size of your model, I'm assuming you have enough GPUs that you are venturing. But nonetheless, the point is that if you have a huge model with a huge dimension size and the heads, so that each head and the dimension multiplication is and the weights multiplication takes more memory than is available, either in the forward pass or back pass for whatever you have to do apply, then you have no choice but to start with tensor parallelism.
Mhm. That makes sense. But it kind of feels like that's because that's that extreme where um, it's shrunk the amount that you can put on one GPU down to some level that doesn't even fit on a single GPU. One layer can't fit on a single GPU.
Not just one layer. I think tensor parallelism would be even sublayer. That's where you end up.
Yeah, fair enough. Fair enough. Less than a layer fits on it.
Yeah.
Yeah.
And
That's why I thought it was kind of an extreme thing that you avoided.
yeah.
So
And then the other point is that uh shoot, I was going to say, so the large model, so yeah, so it's not the GPU limited, it's the RAM limitation then, more like that, because I'm assuming people who are trying out those bigger models are not limited by RAM, but sorry, by GPUs, but more by the RAM within a GPU.
they
Yeah, so most configurations are RAM limited, and you're using parallelism schemes to split the memory load amongst those GPUs. When you get to that sort of like 1,000 plus, 500 plus GPU range, then you might actually be at the point where you have the luxury that you can fit things. Now you're just trying to choose between, do I crank up data parallelism another factor of two, or do I to get more throughput faster,
Yeah,
right?
what I
Right.
meant was, sorry, I maybe my comment was not clear. What I meant was that the size that is limiting you to force you to do tensor parallelism is the GPU, single GPU memory limit. Because if you cannot do your matrix
Yeah,
multiplication on a single GPU, then you have no choice but to start with tensor parallelism.
Yeah, I don't know if you guys can see my screen. I tried to make this a little bigger, but
we can.
modern HTML things resize automatically. You can't just make them bigger. But so for the 80 billion parameter model, they said on a single node with 8 GPUs, so this is 640 gigs of RAM. It was impossible for them to train the 80 billion parameter model. And if they had two nodes, so 16 80 gigabyte GPUs, it was impossible for them to train it. Okay. Now we're not talking about quantization. Yeah. Okay. This is just, the regular model. Okay. So finally, with 32 H100 GPUs, they were able to train it. And you can see, Roger, here that this is where they went tensor parallelism 8 because of what Dave's saying. It's like, I needed to max that out just to spread it out to fit this thing. But if you double the number of GPUs, you'll notice what they do here is they immediately cut tensor parallelism from 8 to 4, right? So they're trying to use less of it. And for the small model, you see tensor parallelism 1, 1, 1, 1. Okay. So it does seem to be that like the NV link is crazy fast, but still to a certain degree, avoid the tensor parallelism if you can. Yeah. Were there any more questions before we move on? All right. So there's some other cool information they have
Jay,
after they.
Jay had his hand up for a bit. I just want to make sure he got a chance to speak if he wanted.
Yeah, I don't know if I addressed
Yeah.
the question, but happy to take it.
No, I was just thinking about tensor parallelism, and I was just thinking I'm missing something because if, like I think Roger said it, the step one that you were showing, Ted, pretty much all of them, regardless of size of the model, they all recommend tensor parallelism. Even if you look at the 10B parameter thing, which was kind of counter to the diagram you were showing later. So yeah, so I'm still not sure about this tensor parallelism, the need for it or when to use it.
Yeah, I can't say that I'm the expert. I spent some time reading the article carefully, but
Yeah.
uh, um,
I mean, basically, why do they so heavily recommend tensor parallelism in the text, I guess?
s- maybe
I,
like I think I wrote a comment like maybe that is the reason because like tensor parallel. So it's like you mentioned NVLink is really fast, but like when you're doing between nodes, like as the Murali also said, like it's slow. It's like order of magnitude slower than that. So when
Hmm.
you're doing tensor parallelism, you're always communicating inside a node. You're always using the NVLinks. But when you do pipeline parallelism, you have to, when you go from one node to another node, you have to add like extra communication overhead, like which is slow. That's why I
I
think
see.
the
I
people
see.
recommend.
I see. And then, so yeah, and then the TP equals 8 is assuming 8 GPUs per node, I guess.
mhm.
Yes. Yes.
Yeah,
Yeah.
yeah, and
Okay,
you'll
that
never
makes
see them use 16 tensor.
right.
Actually, no. Here, they did actually in this one case go to tensor parallel 16,
Mm.
um, but yeah, generally speaking, you uh, uh, you're paying a cost. I think what happens is here at 64 nodes, so 64 times 8, uh, uh, what is that? 512
Yeah.
Hmm.
GPUs.
Yes.
When you get
Yep.
to 512 GPUs, then I think you finally start reaching the point where you can say, I've I'm now just running less efficiently in order to reduce wall clock time, right? So
Hmm.
I double the number of GPUs and the time it takes to train only went down 15%. It didn't get cut in half like I wanted it to, right? But I'll take the 15%, right? And if I had another double number of GPUs, maybe the training time only goes down another 10%. So you're starting to get quite inefficient, right? You're just throwing things at it. But
Hmm.
nevertheless, I can't remember if I said this in previous weeks. If your boss is like, here's 100,000 GPUs, do you want to wait 3 months? Or do you want to use all of them and get it done in 1 month, even though you're extremely inefficient, right? You used 100 times more GPUs and it only was a third the time. But if your boss is like free GPUs, I guess I would do it.
Yeah. Cool. Yeah. And it looks like the pipeline parallelism comes into play only for the pretty much only for, well, they do have PP equals 2.
Yeah.
Okay. Yep. But
Yeah,
that
it's
helps
hard to
actually.
tell. You can see it goes back and forth, 4 and then
Yeah.
1 and then back up to
Right.
2. And
Right.
it may also be in some cases that the difference between the one they showed and the one that had pipeline parallelism 1, maybe it was only like a 1% difference in speed, but they're still just
Right.
reporting the absolute fastest one. So,
Right. Right. And
maybe
it's
you
and
would be like, for all the effort it takes to implement pipeline parallelism, I don't need that 1%. It would actually be a lot. My life would be a lot easier if I didn't use it.
right. Right. Yeah. And clearly for the 80 80 billion parameter models, all
Yeah,
of them have heavy pipeline parallelism
yeah,
at the PP.
and
Yeah.
they all have tensor parallelism. I mean, again,
Right.
you are definitely splitting that really large model. And by the way, I think it might say in the caption, I think this is for 4K sequence length training.
Okay.
So not exactly right, but if you go to 16,000, you quadruple the memory requirements almost. And
Hmm.
so that means that it's impossible to train it not only on 2 nodes, but it would be impossible to train it on 8 nodes with
Hmm.
any combination of parallelisms.
Yeah. Yeah.
Right. But that is why
Yeah.
people use, LoRa, QLoRa, whatever. But I think they're talking a little bit about like pre-training. And so typically for that, I don't know that you could use LoRa for training from scratch.
Yeah.
you know. And then by the time you raise the rank of your LoRa, you have lost all of your savings and you're just as expensive as the regular model.
Yeah. Yeah. One other thing is, if you go between nodes, I know that on AWS they have this thing called EFA, Elastic Fabric something adapter or something. So basically, you put all your you put all your um, nodes close to each other or something. I don't know exactly how
Yep.
they do it.
Yeah. No,
Uh,
all of
Is
these
is
recommendations change depending on your hardware and how fast your communication is.
is there other things besides that? Like if you want to do it somewhere else, because this is, I think, AWS specific thing, but is there something that you could do? Like if you had those tens of millions of dollars, like you could do you could do by yourself, or what is required here? Because NVLink kind of is easier, it seems. It's just something that you get from NVIDIA and you put it in there. But what about between nodes?
I'm trying to remember, maybe somebody else can help me. If I remember in the Llama 3 Herd of Models paper, they actually said that um, they, they use some different communication just because they found it was better than the like whatever um, officially endorsed stuff. I don't know if
Mm,
I'm remembering that right, but yes. So the idea here was for us primarily to talk about the different levels of parallelism and where that overhead comes from. But
mhm.
yes, the trade-offs between them, it will depend on the size of your model and it'll depend on your hardware.
Yeah.
So the intent of the article isn't to say like these are the hard and fast configurations you should use, but they did want to show you for their particular set of hardware. Here are some examples so you can see the nature of the different uh, ways things shook out.
Yep. Cool.
Yeah, Dave, get your hand raised again.
Yeah, so basically I had my hand raised quite some time back, so now I have three, four comments based on the discussion. So very quickly, so when you said that when you go from 4K to 16K context, isn't your well, your memory will quadruple, but if your dimensions also went up, so it can go because of D square
No, I'm saying the
requirement.
exact same model, just going from 4 to 16.
Okay, so you're just saying context length is more, but the model is exactly same.
Yeah,
So
and because the model ends up being the where is our um because the model, is the small part and ends up that the purple, the activations is the biggest part. So when this thing quadruples, the whole thing does the total grand total doesn't quite quadruple. But if you have four things and the biggest of the four things quadruples, then you're really paying the price.
yeah,
So it's approximate, but I'm just saying that like
yeah.
long sequence length really for an LLM really really kills you on training, and I had never really thought about it until recently.
Yeah.
It kills
No,
you
that's a
even more than the bigger model does.
yeah. So the second one was about the tensor parallelism. We had a lengthy discussion. So I think people have mentioned that, but if I'm not, if I paraphrase just for my understanding, so essentially it's a trade-off between other parallelism available, and you are trying to figure out whether tensor parallelism will make sense or data parallelism is, because any other parallelism comes with its own uh, on overheads, communication overheads, versus tensor parallelism will also have communication overhead, but then uh, if you're not using pipeline parallelism or not able to leverage pipeline parallelism, then maybe you want to start off with tensor parallelism anyway, because that's how you will end up, splitting your operations across multiple GPUs. And one possibility is you split layers, so that way each layer is doing its own, each GPU is doing its own layers, tensor multiplications or whatever it is. But if you are not able to fit the whole layer on a single GPU, then maybe you're better off to start off with the tensor parallelism to split the attention heads or whatever else makes sense, I guess. Again, these are like all the trade-offs that one has to consider, all the costs for communication and other factors that, depending on your model architecture. So the third one was, I know we discussed context parallelism or sequence parallelism as one of the options, but in that diagram, did it show up in that chart?
Let's look at our recommendations again.
And maybe to refresh, when do they discuss doing that? Because that's one of the, that's the fourth dimension, right?
So it looks like, it looks like this is sort of their last choice. My guess is that that ring attention is clever, but at the end of the day, it's relatively inefficient.
Oh, it's the
right?
special considerations there, right where your mouse is, right below that.
Mhm.
Right
So
before
for very
mention of
long
it. Okay.
sequences, you really have no choice. Okay. And ring attention not only um, um, I don't know how to say this the right way, but the cool thing about ring attention is it dramatically lowers the amount of memory you need in total, because what you're doing is you're sharding the keys and values across all your GPUs, and then they're passing around in a circle. But at any point in time, each GPU only needs 2 sets worth of keys and values. So if you had 16 GPUs in a ring, then basically each GPU only needs like 1/8. Um, and if you had 32, then they only need like 236, 1/16, right? So it can really dramatically reduce the memory utilization there. But the problem is if you have 32 GPUs in a ring, it requires 31 sequential communication steps. So my guess is all these other things, they have communications, but at least they're kind of getting it all done in 1 or 2 communication steps. And so 31 communication steps probably is slower. And that's why you don't see context parallelism show up until you basically have no choice.
And about the question regarding the inter-node communication, I think Murli mentioned in the chat something like NVLink 3 or Ethernet. Where does the InfiniBand backplane come into picture? Is it for intra-rack only, or some other architectures or some other configurations? Because I thought InfiniBand is what they use for, definitely for inter-rack.
Yes, sorry,
Yeah.
I misspoke before. Like NVLink is between nodes and InfiniBand is for within a single node. I said like NVLink is for within node. Sorry.
NVLink is within a node that's
No, it's internode, like it's between nodes. But you used to communicate between nodes.
Oh yeah, when I say within, so each node is 8 GPUs. That's how they define it.
Yes.
So within a node, they have NVLink, but I think the DGX or whatever that 64 nodes system is, that has the NVLink tree. So it can talk to each other through NVLink. If I'm now that Murli also mentioned that, and I do
she
recall,
mentioned.
I do
Yeah, I
recall
thought it
something
was
like that.
I thought NVLink was typically kind of 8 ports, but it sounds like it's getting to where it's much more. So if it's also being used between nodes, then
Yeah. So in their DGX system, they do have between or whatever you call it, the whole rack is probably the DGX or whatever I don't know how they define that DGX, but they have within intra-node communication through NVLink 3 or switches people are writing up there. And I think to go between rack, they have InfiniBand. And the throughput probably, because of multi-hop between nodes may go down. And then if you're going between racks, it may go down further, I assume.
All right. Well, if you guys are okay, I'm gonna maybe kind of pause the conversation here. I apologize if I at any point misstated the names of the different NVIDIA technology. I'm very this is very much not my area of expertise. But what what the lesson we're trying to talk about is you are going to have different speed communication depending on your particular brand and your architecture. And so in this case, what they found was within the 8 GPUs on a node, they could do a lot of communication relatively inexpensively. But as soon as they went between nodes, then the cost went up. So if you're really lucky, you get something bigger and you can have really cheap communication up to 32 or 64 or whatever the number is. But at some point, you're still going to have this phenomenon that you're going to have a hierarchy, and that's ultimately what they're trying to address in this article is that you you are then going to want to make choices. And so, for example, tensor parallelism. Once you have to go to the more expensive communication layers, you're probably going to want to avoid, right? And all of these parallelism techniques, when you start going to the more expensive, eventually, as you scale up, they really start to degrade. You're no longer getting anything close to linear scaling. Those places where we saw a 40% performance penalty on linear scaling, like that's a pretty big penalty. So I think that's the takeaway, regardless of the specific thing. I was watching the GTC keynote, and Jensen was talking about whatever at one point around the middle, he's saying, okay, and here's our 2-year roadmap. And so I think basically what he was saying is like, hey, right now you can have this many with the really fast communication. And so like a year from now, it's going to be 4 times as many GPUs with the really fast. And a year and a half from now, it's going to be 8 times or 16 times as many. So that's all good news, because eventually, right, if the models don't get bigger as fast as NVIDIA can build these suckers, then you might be able to fit your model on the number of GPUs that are sort of within one fast node, and then you don't need to resort to the slower communication. So I think that's sort of what would be ideal, is if you can manage to stick to within that size. All right, we have a little bit of time, and so yeah, so but mostly gradients. The question in the chat, mostly it is the gradients that are being exchanged in order to it unfortunately it does depend on the different things. And so I think we talked about it in a little bit more detail when we went through the last 2 weeks. So you can go through the recordings for that, but it does vary a little bit, depending. But generally speaking, what happens is the backward pass is where most of the computation happens, and it's where aggregation needs to happen in order to get the overall gradient for each weight. And so generally speaking, that's where you really pay the penalty. On the forward pass, like I was saying, that's just inference. You can really slice things up in the forward pass, and doesn't really require that much communication. It's pretty cheap. It's pretty easy. All right, so a few other things at the end of this article. So after they then, talk about dividing things up and the lessons that they learned and whatnot, they say, hey, let's go back and talk a little bit about like GPUs and floating point formats and a few other things that are I don't know if if they're basics or whatever, but they're very related to things. And so they say, hey, what the heck is a GPU anyway, right? Um, and so I, didn't know all this. And so basically, if it's something akin to like an NVIDIA GPU, what you can think of it is you have these streaming multiprocessors, and they have multiple computation units, and they have multiple levels of memory that they're going to access. Um, I talked to a few different vendors about AI accelerators for things like edge devices, and the architecture for those is very different. They do not have this sort of central bus generic streaming multiprocessor architecture. They tend to have uh, memory and compute located next to each other, and you just sort of pipeline them together. And then the data comes in one end and it goes through a bunch of these and then it pops out the other end. So this is very much talking about your data center type GPU architecture.
Hey, Ted.
Yeah.
Quick question. I don't know if they cover it later, but the term warps. So within the SM, the cores, you have a number of cores that are all executing the same instructions, right, with different data.
Mm-hmm.
But is it the case within an SM, you can have multiple warps, multiple groups of cores that are working together? Is that right?
I thought there was a sentence in here where they said anything is theoretically possible, but you get the best performance, the best throughput if you have all the cores just doing one thing, right?
Okay.
That's going to be the most efficient use of
Okay.
that streaming multiprocessor.
Okay.
Trying to keep an eye on the chat to make sure there aren't questions that they're all getting answered. Okay. And so a lot of what we now see in the last, I don't know the exact number, but I'll call it 2 years, maybe it's 3 years. I don't remember when flash attention first came out. But at one point, everybody talked about how many flops do you have? How many computations, how many multiplies do you need to perform? And it turns out that actually these cores, when they're doing matrix multiplies, can dance matrix multiply circles around memory loads. So it turns out that actually, if you want to know how long something takes to calculate on the GPU, it's really no longer about the number of flops. Now, obviously, in the limit, it is, okay? But if you're talking about which algorithm is more efficient and less efficient, usually the bottleneck isn't how many flops. The bottleneck is how many memory accesses, and are the accesses coming from this cache or the accesses coming from high bandwidth general global memory? Okay. And so that's one of the points that they were trying to make.
Hey, Ted, do
Yeah.
you have any idea about the performance, relative performance between that L2 cache and memory?
I thought they made a reference in here, but it's been a few weeks since I read it. Anybody else who knows can chime in.
I'll just look it up later.
But I
I'm
think,
just curious.
I mean, we're talking like an order of magnitude slower to do HBM than that L2 cache.
Okay.
And I think it's a little more than an order of magnitude. So it's a really big difference. They have some things here about like, woohoo, I can write some Triton. I can write my own CUDA kernels. Not planning to do that, but it did make it actually sound a lot more approachable than whatever idea I had before I read this article. So that's kind of nice. And so this memory coalescing idea is the idea that if you can, actually, was it this here where they're,
Yeah, I see it right there in the center. 32 threads. A warp is 32 threads.
yeah.
MD.
And so here they're still talking about grabbing things from DRAM, from high bandwidth memory. But they're saying, hey, at least if you can grab stuff together, that's better than just trying to gather scattered things around. Okay. But then I think then after this is when they start talking about, but we're going to go even more efficient now and say, what if we can grab from the cache instead?
Hey,
Um,
Ted, in the diagram, they showed the shared memory. What's the difference between that and they showed a link for shared memory? I don't know if they showed the link for shared memory or across SMs. That
you're
part was.
you're talking about this very first diagram, right?
Yeah, you see that SM to SM, it says 7 times 7x. Oh, so that's 7 times faster than global memory. I think that's what it means, right? So between SMs. But
Yes.
what is that shared memory and uh, why is it called shared memory? Like, is it shared within an SM or not across SMs, right?
I
I
think
presume.
what I think what they were saying, okay, is that this shared memory is physically distributed across the SMs, but that it can be addressed globally. So, in other words, this SM can ask for something that's physically located here, and it'll get it 7 times faster than if it was pulling the same thing from global memory. Like right, if you assume everything's in global memory, but then like this first one pulls it in because it wants to do an addition. And now this one wants that same chunk of a tensor in order to do a multiplication. It would be 7 times faster for it to go grab it from streaming multiprocessor one than it would be to just reload it from global memory like it could. I think that's
So
what
I
they're trying to.
see 5 layers then, right? From global memory to L2 to L1 to shared to registers.
Yeah, yeah, that sounds right. Although registers are probably pretty small. They're probably hard to optimize except within like an operation.
Yeah, but I think
And
registers
you,
possibly maybe shared across cores. So they, within an SM, let's say it has
Mhm.
128 cores or whatever number of cores it has. So those many registers
Yeah,
or maybe more, two
yeah,
per
yeah, yeah, yeah,
core or whatever,
exactly. So
something
that,
like.
so right, that's why I'm saying like within like a matrix multiply, if you're doing some kind of multiply, accumulate, multiply, add thing, then these cores are probably accumulating to certain registers very efficiently, the way you're talking about sharing them, right? So like I could theoretically be um, multiplying certain rows, and this guy could be multiplying other rows, and they could both be accumulating them to the same register, I think, as like a common matrix multiply technique. And by the way, anybody else who knows this stuff better than me, feel free to chime in. Um, but so it was nice to see them include, some of this information digging down into the GPU. Um, so they're saying, yeah, so contiguous memory access from high bandwidth memory is definitely much faster than if you're just kind of pulling from different places. So they say here something like they got a 10 times improvement by doing this. They talk about tiling, and I think um, tiling does two things for you, right? So one is, of course, you're pulling contiguous chunks, but if you can cleverly sort of reuse for a while um, uh, information that's in a tile, then that's more efficient than going and grabbing this part, throwing it away, going grabbing other things, and then at some time later needing to read from global memory again to get this same thing, right? So it's a little bit like I'm just trying to think like if you had a task you were doing at home, like um, I don't know if you guys ever read Algorithms to Live By. He had a story about like his college roommate, I think it was, and when he was matching socks, he would basically like pull sock out, and then if it didn't pair, he would just like throw them back into the laundry basket and just keep doing this, and it was like very very inefficient versus some. any other scheme you can imagine where, you're sort of hashing and whatever, building up, something. So yes, so tiling, especially for things like matrix multiply that are structured, there's predictable ways in which you can minimize the number of times you need to load a particular tile, if you do things efficiently. And then there's this interesting thing, the thread coarsening. Like what? So where do they say? So we can apply a technique called thread coarsening, which involves merging several threads into a single coarsened thread. Okay. And so then the idea is you actually don't want lots of little independent threads doing very tiny amounts of work and each asking for memory, right? You'd rather group them into gangs and say, ask for a big chunk of memory and do a bunch of work on it. Don't just be constantly asking for lots of little things. Minimizing control divergence. This is, I believe, the thing where it says, what I was talking about with your question, Roger. So control divergence occurs when threads within the same warp take different execution paths. One obvious thing is if you have an if statement.
Mm-hmm.
Okay. I imagine that you could come up with some example where you have maybe like at the boundary of a matrix at the edge, like in images, we often have like things at the edge of the image or whatever, and you don't really want to be doing something different on the edge or whatever. And that's why we come up with techniques like masking and padding so that they're all actually doing the same thing, but because of the mask, the net result is slightly different. But in terms of like, what cores they're running, they're like, oh yeah, I don't know, I'm just doing multiplies, but there's this extra mask that just, ensures that, yeah, you're all doing multiply, but you're actually, you're not doing multiply in some places, but I don't have an if statement. I just have the mask that, prevents the result from being different. Does that make sense?
So I assume in SIMD, if you have a branch in the code, you have to execute both sides of the branch, regardless of if any cores. In other words, even if nobody takes path B, you still have to execute path B.
Yes, but in a perfect world, I think what happens is a different streaming multiprocessor is doing path B and you're doing path A versus you are doing both path A and B and have to split it amongst your threads.
Right. Or there are some kernels that don't have the condition in there, and you use those for efficiency, and you put the if on the edges where there are conditions.
Yep. Yeah. So that was kind of cool. And then they finally get to this idea of fused kernels, and I don't know if you can tell from this diagram what they're talking about, but it's a sequence of operations that happen from top to bottom. And so some stuff comes from memory, and you do a little bit of compute, and then you take the result and you send it back to memory. But then it turns out that the very next thing you want to compute is that very same thing that you just sent to memory. So you do another read. And so if you look here, the right of the triangles and the read of the triangles, it's the exact same thing. And so this entire round trip was a complete waste of time. And this entire round trip of circles is a complete waste of time. And it's entirely possible that this kind of thing can happen very often. So much more efficient would be you load the squares once, you do a whole bunch of computes, and the rectangles go back, and you never waste time with the circles and the triangles going back and forth. So if you think about if I just think about common code that I write where I might have multiple calculations that I do in a row, I'm going to tend to use my intermediate values right away. Every now and then I need to write them and they're going to get used much later, but I have a tendency to use them right away. And then in certain specific calculations, like a matrix multiply, like an attention calculation, clever people, clever trained reinforcement learning agents, whatever, they've figured out, well, what is the access pattern that minimizes the number of reads and writes. And so this is where we get to flash attention, where we do tiling, and we do have these queries and keys, and we need to do these dot products in order to calculate attention. And there's an accumulated version of the softmax calculation that's performed. But it turns out that flash attention is really awesome because not only does it reduce the number of reads, partly by doing some recomputation, but the other thing that happens is a little bit like the ring attention algorithm, where it actually reduces the overall amount of memory that you need in total. Similar to ring attention. In ring attention, if you had 16 things and you're holding one and you're passing the other ones around, you really only need 2x, even though in total you have 16x. So there was flash attention 1, and then I don't really know the subtleties of version 2 and version 3, but we get big improvements again by this pattern of reducing these intermediate writes, which then just sometime soon get followed by reads. But then we also allow ring attention. We reduce the total amount we need. Yeah, question? Comment?
Yes. Like from this conversation, it seems like if you're compute bound, that's more efficient than being memory bound, right? It's always like good to be compute bound.
Yeah. So it's like you can do like whatever. I'm going to slightly exaggerate, but it's like hundreds of thousand matrix multiplies in the time it takes you to one memory feed. So you want to be compute.
So if you think like that, then like isn't KV caching pointless? Like at inference, like that's like a common technique for. I think you guys talked about it before.
So I was trying to do some math, and I think the issue with KV caching is that if you were to load the token value and multiply it by the W sub k matrix in order to calculate the key,
Okay.
the size of your token and the size of your weights is the same size as the keys that you're caching.
Oh, okay. So you reduce your memory.
So it's not about the computation. It's about the fact that those things actually take more time to read than the cached keys and values
Yeah,
themselves.
that makes so much sense. Like I've been like struggling with this idea for a while. Like if we want to be compute bound, then why do we cache them?
Exactly. Yeah. No, I was thinking the same thing. I'm like, well, wait a second. Recomputing it can't be that costly because right,
Yeah.
flash attention does like whatever 10-15% more
compute.
multiplies, but it reduces the memory load. So you would think that and then it's because actually the keys and the tokens are the same size. So tokens plus weights, you're doing more memory loads and you're doing a multiply versus just load the darn key.
Thank you.
Yep. All right, we're pretty much out of time, but I just wanted to quickly go through. So they talked about floating point formats and mixed precision training. So basically the idea is we started very quickly coalescing on doing all neural network training, and I'm talking about like whatever, 10, 15 years ago, right? In 32-bit floating point, because we had some very large values and we also had some very small values, especially with the gradients, you can get some very small values. And people said, well, everything would be half the size if we just use 16-bit floats. And so they tried using 16-bit floats everywhere, and it didn't work. It underflowed. And maybe it overflowed in some places too, whatever. And so then a very quick analysis showed, in certain places for gradients, we still need the full 32, but in other places we can get away with 16. And then they started using brain floats, B floats, that have more dynamic range because they use more bits for the exponent, but they're more subject to rounding errors. Okay, so yeah, they're like, yeah, the rounding errors are not too fatal. You know, it's like, oh, okay, so we're off by 1/256th or something like that. A complete underflow to zero is much more catastrophic than just a slight rounding error in your number. And so then very quickly, you got PyTorch support for automatic mixed precision between 16 and 32. And then DeepSeek managed to do some stuff with 8. Most of this stuff is experimental. There's a lot of literature for fine tuning where, yeah, you can do LoRa, QLoRa with 8-bit, 4-bit, stuff like that, or whatever. So they're smaller, and obviously it reduces the amount of memory. And if it doesn't even reduce memory, because I was actually very surprised to read, I don't remember if it was here or somewhere else, but that mixed precision, actually, the standard form of mixed precision uses the exact same amount of memory as regular 32, because you have in some places 32 and 16-bit copies of the same thing. And so that extra negates your savings. But matrix multiplies for 16-bit are approximate, almost exactly twice as fast as matrix multiplies for 32-bit. So even if you don't save memory, your training run still finishes like in half the time. So that's why people use mixed precision, not for the actual memory savings. But if you go to 8, then you start getting more memory savings. Yeah, Roger.
I just wanted to make sure I understand correctly. So float 32, float 16, those were like standard hardware implemented FPUs in the GPU, right?
Mhm.
When they introduced bfloat 16, I'm under the assumption they must have it required like a hardware change. Like they
Absolutely.
added a new core to it.
Yeah.
Or not a new core, but a new
Yeah. No,
piece of
when
FPU.
bfloat first came out, it was like, I don't even remember, but like bfloats you can use on a TPU and you can't use it on an NVIDIA GPU because none of them supported it.
Okay.
But then immediately the next generation of NVIDIA GPUs supported
Added it
bfloats.
in. Okay. And
And
presumably the float 8, the E4M3 and E5M2 are the same way then.
yeah, my understanding is that these are fairly new formats.
Okay.
And I don't know if it's only Blackwell, but like there's really not a lot of support for Float 8 yet.
Okay.
I believe it is Blackwell only.
Yeah. It's not that you can't do Float 8, but it might not be fast because it doesn't have, the full support.
Yeah, it needs the hardware support. I'm almost surprised that the hardware guys got on board that quickly with new numeric formats.
Yeah.
And maybe it's just that a 16-bit floating point unit doesn't take a lot of real estate. But
also, NVIDIA has a monopoly and they've got whatever trillions of dollar valuation. And so like, throw the kitchen sink into each GPU, whatever the cost, just to not give anybody a reason to use something else.
Yeah, although you need to wait around long enough to make sure that this isn't just a fad and it's going to be replaced immediately by something else, because there's a longer lead time for the silicon, right?
Yeah, I suppose that's true, but yeah, I mean, if you think about it, right, like if it has support for all of these for doing matrix multiplies in any one given model training that you're doing, you have big chunks of the GPU you're not using.
Yeah, true.
Let alone, like I have a PC with a consumer and it has all of the video game functionality that you never use when you're training a neural network.
Yeah.
All right, I think we're down to the end. Oh, some nice visualizations here, again, showing you the range, the width, but also the level of granularity within that. So, cool. And then I think, yeah, so then that's kind of getting to the end of this article. They have this diagram, which I think maybe is from the Llama paper. And they talk about, hey, we're using 4 different degrees of parallelism. If this diagram works for you, great. Personally, I found this diagram not to be terribly helpful because it's really not like drawn to scale. It's just sort of saying like, hey, look, if you look at all the TP zeros, that just shows that tensor parallelism is spread out. And if you look at all the DP zeros, they're spread out. And if you look at all the CP zeros, they're spread out. And things are spread differently. So if this diagram works for you, that's great. Didn't really do much for me.
One thing it does make me notice though is that the CP, that's what's kind of that's what's driving the TP0. Is that right? So so you need to have the CP for the longer context. Is that right?
Well, like basically, if you've ever done one of those logic, like like ands and nands and XORs or whatever, if you've ever done one of those, and if you just did it with 16 entries, like 2 to the 16th,
Yeah.
right? So you're gonna have like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, right? You're gonna have all 16 combinations of zeros and ones. So that's basically what I'm seeing here. It's just you have all 16 combinations of zeros and ones.
Mm-hmm.
So what is kind of not very clear in this picture is the GPU numbering, because while you have TP0, TP1 and all that, but then the GPU numbers within the node is like, maybe it is 0, 1, 2, 3 going like that. The next one is 4, 5,
one is 3, and then 4, 5, 6, 7.
Okay.
So yeah, I mean it's an okay diagram. If this makes sense to you and it helps you understand, that's great. It just didn't really, what they're trying to show is that the different dimensions are orthogonal, and that's a good point to be demonstrating. It's a difficult thing to show on a 2-dimensional figure, and I don't know that they really blew me away with the way they.
So one thing, if I may, Ted, so I think to Roger's point, right? So when you go from 1 to 2 GPU, they initially do TP0 and TP1 and not DP0 and DP1. So let's say you had only 2 GPUs, GPU0 and GP1. So they actually do TP0 and TP1. And then let's say you add in multiples of, you double every time. So now let's say you go from 2 to 4, then you're adding CP0 and CP1. And then you double it again, then now you're adding PP0 and PP1, and then you double it again. Now you're adding DP0 and DP1.
That's true, and I don't know that that's actually the order in which you would add them.
Well, assuming GPU numbers relate to that, but anyhow, yeah.
Yeah, that's why I'm saying this. All right. So anyway, so we're at time.
Yeah, I was just going to say that it just looks no more than just ordinary indexing on a 4D vector.
Yeah, yeah, because this
This
diagram doesn't in any way infer where the faster and slower communication is or anything like that, right? It's just 4 different orthogonal dimensions.
Right. I mean, here it's like you just go 0, 0, 0, 0, 0, 0, 0, 1 and just keep doing that, and then you just end up with this diagram, basically.
Yeah, exactly. Right. Yeah, and I don't unfortunately think that the order of them you can really infer about communication patterns or whatever. And even if you did, it's just specific to whatever hardware that they happen to have that they were training this on.
Yeah, I think they have more details in how they figured out the numbering, but that's okay. We don't have time for that.
All right. So we spent 3 weeks, and hopefully this is insightful, a little different from some of the theoretical stuff we're talking about how to calculate attention or this or that or whatever. And again, if you're interested in inference, all of these 5 parallelism techniques do also apply to inference. And in fact, they're much easier. So this is also transferable to inference. It's the other direction, going from inference to training parallelism. That's actually much harder because of all the memory and the back propagation, like I said earlier. So hopefully you guys had fun. I think the people who worked on this Hugging Face article, and I guess they're going to publish it as a printed paper book that you can buy and put on your bookshelf. I think, they did a good job. They're bringing stuff together from different papers and different articles. And so we've seen that like sort of the color schemes or the naming schemes or the whatever are not always consistent 100% when they're talking about different concepts if they happen to be pulling from different papers. But still, I think that they did a really good job with lots of illustrations and good examples. So kudos to them for giving us this really cool, very long article for us to talk about.
And thanks,
Yeah.
Ted, for going through this.
Yeah, kudos to you, Ted,
Yeah,
for
for
taking
finding
us
it.
through this.
I'm going to go ahead and stop the recording then right now.